This is Chapter 4. We're going to do Section 1 and Section 2.
To move the piano, one of these students is pushing it and the other is pulling it. Each student is exerting a force on the piano. A force has both magnitude and direction. It is measured in units of newtons. The student on the left is exerting a force of 25 newtons to the right. The student on the right is exerting a force of 20 newtons also to the right. Together, the students are exerting a net force on the piano. This net force is an unbalanced force on the piano and causes the piano to move to the right. An unbalanced force is always necessary to move an object from rest. An unbalanced force is also necessary to change the motion of an object that is already moving. Balanced forces cause no change in the motion of an object, whether it is moving or at rest.
So going back, summarizing what they were talking about, and that they were talking about balanced and unbalanced forces. For instance, if I put my hand, my desk is pretty much, it is attached to the ground, and I am applying a force on it, okay? But is it moving? It is not moving. So is that a balanced or unbalanced force? It's a balanced force, okay? So you do have to have some type of movement to show an unbalanced force. It gives you the definition for force here. It's an action exerted on an object which may change the object's state of rest or motion. You can also change directions with this. It does cause an acceleration, and the SI unit for force is the Newton. And they can act through contact or at a distance. And before this section is over with, we're going to talk about contact forces and field forces. And field forces act over a distance. It can be short or long distances.
Is only from the physical contact of two objects. Other forces, called field forces, do not require physical contact between objects. One example of this kind of force is gravity. The earth exerts a force on the ball, even when they are not in immediate physical contact. Consider the baseball again. Other than the bat, what else does the ball come in contact with? The air. As the ball moves, it comes in contact with molecules in the air and experiences friction. All forms of friction are contact forces.
Okay, so let's talk real quick about what he was talking in that one about the contact forces and field forces. Automatically, whoa, that's not what I want. What was example of contact forces? Huh? Okay, the bat hitting the ball. Anything that creates, we're going to talk about friction here. If it's a frictional force, it's considered a contact force. So even the air hitting the bat created a frictional force, which is considered a contact force. What?
Is this where you have like the car and you have all that, and we have to draw that on the test?
Yes. Yes. Then you've got what is called field forces, and we're going to look at 4 field forces. The first one for field forces, he mentioned, do you know what he mentioned? He mentioned gravity. So gravity is considered a field force. Nuclear forces. You have weak nuclear forces and strong nuclear forces. Where do you think nuclear forces are found? Within the nucleus of an atom. So when we said field forces act over a distance, that is an extremely small distance we're talking about. But if you remember back when we were talking in chemistry, we said that's the only way that the nucleus can hold itself together, because you've got protons and neutrons in there. The only charge you have is the charge of the protons. And if all of those protons are tightly packed together, and they all have a positive charge, what do they want to do? They want to repel each other. So the additional neutrons are in there. Even though the neutrons do not have a charge, they do help supply what is called a nuclear force, so that the protons can stay closely packed within the nucleus. So you've got strong and weak nuclear forces. That's within the nucleus of an atom. And the last one is electromagnetic forces. Electromagnetic forces. And we will look at like an electric field. Can anybody give me an example of an electromagnetic force? Okay, could be a magnet. What about static? Okay, static is going to help create an electric field too. So those are even other forces. So contact, just the word contact itself is pretty evident. If you've got two objects that come in contact, that's a contact force, and friction is also considered part of that. Looking at changes in motion, we are going to have to do some more drawing. We're going to be drawing stuff that's called force diagrams. This is going to show your force diagram. The arrows that you draw are going to have to show magnitude and direction. So the longer the arrow, you're telling me that that force has more magnitude than something with a short arrow. And we've already talked about vectors before. So the diagrams that show these force vectors are called force diagrams, whereas force diagrams that show only the forces acting on a single object are called a free body diagram. I do want to call your attention to those last two bullets, this one and this one. A force diagram is different than a free body diagram. And when you have your homework or worksheets or the tests that you'll have over this, if it says draw a free body diagram, that is what are my forces on one single object. But if you're asked to draw a force diagram, then you're going to be drawing a diagram of everything that is represented, the forces that are being applied and whatever's applying the force, what is it applying it to. So you can have multiple objects there. We're going to look at the difference between the two. This is a force diagram. Again, it is showing all of the forces that are acting within the whole situation, the car and the wall, the car hitting against the wall. The vector arrows represent all the forces acting on a situation. If I asked you to give me a name for these forces, what would you give me for this one for the car that is pointing down? The force of the car pointing down. Force of gravity. What about the force that is pointing straight up? What is actually pushing up on the car?
I was going to say that's the opposite force of the gravity.
Okay. What is pushing up on the car?
Air. Isn't it? Because it goes in the car.
Well, the car is on what?
Car's not a glider, bro.
It's on the ground, okay? So that's the earth. So you've actually got the force of the ground or the force of earth, I don't care which way you put it, is pushing back on the car. Notice since the car is just sitting there on top of the earth, the magnitude of those two forces are equal, right? The length of the arrow is the same. They're just pointing in opposite directions. So is that a balanced or unbalanced force? It's a balanced force. You've got another arrow that is pointing backwards. This one that is pointing backwards, that is due to resistance. Multiple ones. Resistance due to air, because it's probably having to push air out of the way. Frictional forces, the tires hitting the pavement trying to get it to go forward. That's another type of resistance, and then obviously it's going to hit the wall too. Right? So that is resistance, and you can have multiple things that fit within resistance. Looking at the wall, again, you've got force due to gravity, force due to the ground. Those are the same magnitude, opposite direction. And then what do you want to call this force that is pointing forward? Okay, since the wall you assume is stationary, that's going to be the force that the car is pushing against it. That is a force diagram. You look at everything within the situation and you label all your forces. Now, if I asked you to do a free body diagram that only shows the forces on our object of interest, in this case, what's probably more interest, the car or the wall? What do you think?
Car.
It's going to be the car. So if I asked you to draw a free body diagram of just the car, it's just one half of what you've already seen. Okay? Still the same labels: force due to gravity pushing down, force of the ground or earth pushing up, and then force of resistance. That's what is going in the opposite direction of the car. So resistance is typically opposite direction of whatever force the car is going to be doing. Let's watch one more video out of this section.
Motion or potential motion. In this case, the toy is being pulled uphill. The motion is up the ramp, so the friction force is down the ramp. If we let go of the rope, the toy will slide downhill. Friction now points uphill. The final step is to add up all the forces. For this situation, the best choice would be to break each force into its components parallel and normal to the ramp. You can then find the net force on the object, and therefore the change in motion in both directions.
So again, I know I've told y'all that breaking these components that aren't at 90 degrees, breaking them up into 90-degree components for whatever vector or resultant that you have wasn't going to go away. And it's still not going away. I know we started off with some real simple stuff. Everything was 90 degrees or 180 degrees. But we will, by the time we get through with this second section today, get into some of these where you're going to have to break them into components. A couple of things I wanted to point out here. Again, force due to gravity is always straight down. Even though our duck is on an angle here, force due to gravity is always straight down. Your normal force, that is what this F of N is. Your normal force is always perpendicular to the surface. Perpendicular to the surface that your object is on. So our duck was on a ramp, which was at an angle. So you notice that our normal force really is at an angle compared to what our traditional XY coordinate system is. Because if I draw out the traditional XY coordinate system, you know, this is pointed up here. Force due to gravity, that is going straight down. And then even notice the force of the rope, that FR. It's at an angle also. It's at an angle also. Again, force of the rope. Originally we had the rope was pulling like this. That goes with the original force of the rope that was here. What caused this other FR down here?
If you let it go and it slides.
If you let it go and it slides down. Because now you didn't have that extra angle between the ramp and the rope. It was just going to slide straight back down. So the force of the rope there was, the angle was just a little bit different. So really watch the information that you're given. Draw out any of these problems that are given. Come up with a coordinate system that you think would work best. You know, X, Y. But does it need to be tilted or not? And then again, you notice that they did come up with components. Do y'all have any questions? Okay. So this starts section 2, and in this section we're going to talk all about Newton's first law. By the time we get through this chapter, we'll have Newton's first, second, and third laws talked about, plus some everyday forces. So Newton's first law, I know you've heard it before. An object at rest stays at rest. An object in motion stays in motion unless they are acted upon by an outside force. That's what that is basically. An object at rest stays at rest, or an object in motion stays in motion unless acted upon by an outside force. I've just condensed a little bit whatever that very first bullet point says. And then it gives you a brief summary in the second bullet point. It says if your net external force on an object is 0, if F net is equal to 0, what does net mean? The sum of all your forces. If your net force is equal to 0, then what does that mean for acceleration?
0.
Then acceleration on your object is also 0. Acceleration on your object is also 0. So now we're going back to the same example we looked at earlier in section 1. They've added one more piece to this puzzle, that's force going forward. We talked about the gravity, the ground, the resistance, force going forward, because in the previous section it looked like it was moving forward and is going to hit a wall. The first law refers to the net force, which is the vector sum of all forces on the object. That's what we said. And it says to find the net force on an object can be found using the methods for finding resultant vectors. What do they mean, the methods for finding resultant vectors?
Adding up the components.
Okay, components. Right here in this example, everything's at 90 degrees or 180 degrees. This one is going to be really, really simple. Okay, it's a matter of adding and subtracting things that are within the same plane. So if I look at it, the resistance and the force going forward, what happens with those?
Cancel.
They cancel. What happens with the force of ground and force of gravity?
They
They cancel. And it has to do with direction too, not only magnitude, but direction. What is going to happen if we have an example like earlier where you've got your object that is on a ramp, and now your forces are no longer parallel with each other? It's what Mitch said. You're going to have to break those into components, get everything with an X and Y component, and then you go and add and subtract what you've got to, what you're working with. So if you're dealing with an angle, you've got to use, things like the Pythagorean theorem, sine, cosine, tangent, to resolve it into usable vectors. Try not to look at how this problem is worked out. We'll work it out together, because how the PowerPoint works this out, I like to work it out just a little bit different. I think it just, the way I work it out, the PowerPoint is going to tilt your X and Y axis. And visually, I think that might be a little more complicated than what you can handle at this point. So I will work with a traditional XY axis that are going true north and true east instead of trying to tilt it. But here's our sample problem. Derek leaves his physics book on top of a drafting table that's inclined at 35-degree angle. The free body diagram below shows the forces acting on the book, and it wants you to find the net force acting on the book. Again, net force. You've got to resolve anything that's not at 90 degrees, which the force of the table on the book is not at 90 degrees compared to the force of gravity. It's going to have to be resolved into some components. So we'll go work this out. Redrawing what they had here. Again, you had your angle here. This is our object. What can we call that force? The force of the table on the book. Is that really the normal force?
Yes.
It is. Because isn't it perpendicular to the surface?
Yeah.
It is. So that's really our normal force. We had the force of friction. I'm going to go ahead and draw it. Force due to friction. And they gave it as 11 newtons. And then the force due to gravity, which is moving straight down, force due to gravity is 22 newtons. I'm going to give you some pointers a little bit later on, but when you're working at an angle like this, most of our problems, it is normal for the force of gravity to be a larger component than the normal force. Notice here, is the force of gravity a larger magnitude than the normal force? That is typical, okay, when you're working at an angle. We will run across an example of two where that's not it, and we'll talk about what those differences are. First thing we want to do, it does tell us that it wants us to find the net force on the book. That is going to be what's going on in the x and the y axis. And it says select a coordinate system. And if you look at the next slide within your PowerPoint, you can see where they like to keep the x and y axis tilted. That is not what I want to do. I'm going to go with a traditional x and y axis here. And we'll redraw our components. Okay? Normal force up here, 18 newtons. You've got force due to friction, which is 11 newtons. And then the force due to gravity, which quadrant is it going to end up in? 1, 2, 3, or 4? It's going to end up in 4. And that was 22 newtons. So that's the way I'm going to draw it there. Now, let's look back at our original drawing, because I want to point out angle. This angle right here was 35 degrees, right? The angle that translates to 35 degrees is this angle right here. That is 35 degrees. So make sure you realize how the angle actually translates whenever we move this.
Why is it?
Why? What?
Why is the angle there?
The question was, why does the angle move to there? I'll try to draw it maybe a little bit different. Again, this angle right here, that's 35 degrees. This small angle right there is 35 degrees. When we tilted our axis right here, that angle right there was 35. Okay? That would have been your 35 degrees when I moved over my ramp. So this 35 degrees is the same as that 35 degrees. Just think about taking your ramp that's like this, and now you've moved it to where it's level, so that 35 degrees is now right below it.
Okay, so instead of like the 18 being pointed this way, we moved it so the 18 is vertical.
Yes.
And
I have rotated everything counterclockwise to get my normal force straight up and down and my force due to friction parallel to the x-axis. So since that 35 degrees has now been rotated counterclockwise, that's how it can translate over also. So what I have starred here in pink, and then the other 35 degree star in pink, those are the same two angles. Okay? Okay. Starting back with this. Now we've got two of our forces. I mean, they're right on the x and y axis. Really easy to deal with. The only thing we have to deal with now is our 22 newtons. And we're going to resolve it into its y component and into its x component. Can we solve for x and y now? Yeah. If the angle there in yellow is 35 degrees, what is the angle here in green? Okay, 90 minus 35, I heard 55 degrees. So get out your calculators and let's start working. Cosine is adjacent over hypotenuse. So x equals, and then sine 55 equals y over 22. So y equals. So there's what y'all calculated for x and y. Again, I was just using two significant figures. So for X, 13 newtons. For Y, we've got 18 newtons. Now, at this point, we have our X, we have our Y. We'll draw them a little bit different. X right here is 13 newtons. And then the Y, I know that I've got it written right over here, but really you can write Y right on the Y axis. So do you see how everything is on the X and Y axis now? What do you notice about your normal force? It's going to cancel out. That 18 newtons and that 18 newtons is going to cancel out. So what do we do with the Y component? You know, your force net, without me writing it down, X's cancel. Okay? Sorry, the Y's cancels. The X, 13 minus 11. You get a net force of 2 newtons. What direction is that going to go?
East.
Don't use east because that's not used here. I'm hearing down the ramp. So mention a direction, and you are telling me it is moving down the ramp. So that's how you would solve this problem. No. Yeah, we do have a little bit more to this section. Again, if you like the way the PowerPoint solves this, by all means, look at the PowerPoint as far as their drawing goes. Inertia. It is the tendency of an object to resist being moved, and if the object is moving, it wants to resist a change in speed or direction. So inertia is dealing with resisting a change. Inertia wants to resist a change, either to start moving or if it's already moving, to change its movement. Newton's first law says it's often referred to as the law of inertia, because in the absence of a net force, a body will preserve its state of motion. Now, if we didn't have any frictional force, you know, if you're in a vacuum, once you give an initial force to an object, it's going to continue to move and it's not going to stop. But we don't live in a vacuum. So air resistance, frictional forces with, if you're touching the ground, which is most cases, is going to provide some type of extra force. And it says mass is a measure of inertia. So let's go look at a video.
The kickball is hollow and has little mass. The bowling ball has a lot of mass. Let's apply a force to the kickball. The kickball has little inertia because of its small mass, so a force will cause it to accelerate rapidly. The bowling ball is very massive. Its large inertia causes it to resist changes in motion.
Okay, pretty simple there. What's inertia proportional to? Mass. Okay, so inertia, this thing that looks like a fish, that means proportional to, is proportional to an object's mass. So if it's proportional, the higher the mass, the blank the inertia. The higher the inertia, okay? The lower the mass, the lower the inertia. The two are proportional. This is showing the operation of a car seat as far as the seat belt goes. I don't know if you've ever known exactly how the operation of a seat belt works. I'm sure this may have changed some over the years because this book is pretty old, or the PowerPoint is pretty old that it comes from. But it still works. You've got a large mass that is there at the bottom. Okay? This large mass down here, it is hooked to this pin. And notice that there is a pulley or ratchet system that your seatbelt is actually attached to. And on that ratchet you have several teeth. Does everybody know what a ratchet is?
I have no idea.
Okay. Everybody except Ethan. Okay? Who's ever used a ratchet at home? Never?
Actually, I used one.
Okay. Okay.
Like yesterday.
A ratchet system is basically, it'll have teeth on this one has teeth on the outside. Typically the ratchets you use at home are circular and it has teeth on the inside. And if you pull it one way, it'll tighten up, and then when you pull the opposite way, it'll lock. It stays tight. That way you can keep moving it in one position. And this one right here, if you apply the brakes suddenly, what's going to happen to that large mass? The large mass is going to move forward. This pin that is attached to the mass is going to move its position and engage inside of the ratchet, and it's going to lock the ratchet into position, which locks your seatbelt into position. Okay?
Dude, cars are so cool.
Yes. I knew y'all would appreciate that.
Can we make a seat?
Sure, go right ahead. One more thing. Equilibrium. It says that with the net force of an object is 0, you're in equilibrium, and we've already talked about that. Objects that are either at rest or moving with constant velocity are in equilibrium. So make a note around that second bullet point. That would be something easy to bypass later on. But if you have a constant velocity or you are at rest, you are considered to be in equilibrium. Because even at constant velocity, your force due to friction and your force due to your object are equal in magnitude, just opposite directions. Was our book in equilibrium? The physics book that was on the table, was it in equilibrium? No, it was actually sliding down the table.
Was the car that was driving?
We didn't have the car. Are you talking about just the free body diagrams we looked at? You can't tell because there was no information given. I mean, it looked like the wall was still intact. It looked like the car was intact. So, I mean, it could have been barely pushing against the wall and the wall not moving. Yes, it would have been in equilibrium. But it didn't give us any numbers really to work with.